Good morning, everyone. Today we're going to look at a couple of example problems of full symmetrical parabola projectile motion. All right, so let me explain the two most common ways a problem can be set up. Sometimes a problem will give you the actual resultant initial velocity and its trajectory angle. In such a case, you will need to resolve that initial velocity into its two components for your DVAT chart before you can do anything else. Remember, unless you want to use calculus, the resultant initial velocity is made up of two pieces that are independent of each other. So, if you're given that initial velocity, you must resolve it into the components to put on your DVAT chart before you can do anything else. And the other way a problem can be approached is if they ask you to find the initial velocity and its trajectory angle. In such a case, they will give you enough information for your DVAT chart to find the two components using the general equation. Once you have the two components, then to determine the resultant initial velocity and its trajectory angle, you would use perpendicular vector addition skills. You would use the Pythagorean theorem, and you would use the inverse tangent of the tangent ratio. Now, this first problem we're looking at is actually what I just stated, the second approach. They don't give us the initial resultant velocity, but they will ask us to find it. So we need to set up our DVAT chart, and we're going to first be finding both components of that initial velocity, and then we'll use our vector addition skills. Okay? So let's take a look at this one. We have a kicker who kicks the football down the field such that it travels 60 meters along the field, and it does this in 2.2 seconds. All right, let's first create our DVAT chart. So we have the horizontal side and the vertical side. We have D, V sub O, A, and T, our four descriptors, right? Okay, so now before we look at this and start chucking other stuff in, let's talk about the inferred information. The information they're never going to tell us, but we have to know from the situation, the physics of the situation. On the horizontal side, we know the velocity is constant because there are no horizontal forces to change the motion of a projectile. So we know that the horizontal acceleration is 0. That is one of the inferred pieces of information, so we always put that down. On the vertical side, we know that it has an initial vertical velocity. It decelerates up due to gravity to a stop and then accelerates back down to the ground. Now, that means the vertical acceleration is due to gravity, and we're taking down to be the positive direction, and it always points down. So there is our vertical acceleration. They're never going to tell you that. They're going to expect you to understand it. Finally, the ball starts on the ground, it ends on the ground, and there we go. 3 pieces of information. Notice this is actually quite different from the half parabolas. In the half parabolas, the initial vertical velocity was 0. It started from rest and just went downward. Okay, so what we're going to do is now we're going to read the problem and stick in the given information. So here we go. It says that the ball traveled 60 meters along the field. Well, that would be the range because that's horizontal if it's along the field. So we put that there. The 2.2 seconds is the hang time. Now here's where we have to remember both motions take place concurrently in that time period. So that goes on both sides. Now if we look at our chart, interestingly enough, look at each side. We have 3 knowns, 1 unknown. 3 knowns, 1 unknown. So we can use the general equation on each side and find these 2 components of the initial resultant velocity. So let's do that. Let's start with part A, the vertical component. We're going to use this information, not any of this. This is for horizontal only. This is vertical. So we're going to say the vertical displacement equals V sub O VT. Use subscripts, please. Keep it separate. 1/2 G, because that's vertical, T squared. Now, we want to find the initial vertical velocity. So, let's do some algebra. First off, we do have a 0, so let's use that to help us shorten our algebra. If the vertical displacement is 0, let me use red for that, that drops out. So if we have 0 over here, we can take one of these 2 terms and subtract it over. All right, I'm going to do this one. So we get negative V sub O VT equals 1/2 GT squared. All right, now I want you to notice we have a T and a T squared. So this 1 T cancels with one of those 2 and leaves a single T behind. Also, we have that negative, so why don't we just switch the negative sides? So we get V sub O V equals negative 1/2 GT. All right, so now we can plug and chug. So we get negative 1/2 times negative 9.8 meters per second squared times 2.2 seconds. Now look what happens to the negatives. A negative times a negative is a positive, which makes sense because which way does the initial vertical velocity point when the ball leaves the kicker's foot? It points up, and we've been taking up to be positive, so we're getting a positive. That's good. All right, so now stick that in your calculator, and you should get 10.8 meters per second. Okay, double check that you're getting 10.8. There we go. Not bad. So let's bring that over here and put it right there. That's the vertical initial velocity. Now let's take a look at the horizontal initial velocity. We're going to write the general equation again, but now it's modified for the horizontal side, not the vertical. Okay. Now, on the horizontal side, we have 0 acceleration, so that drops this out. And we're looking for that. So all we have to do is divide the t over. So we get dh over t. So v sub OH equals dh over t. So that's going to be 60 meters divided by the 2.2 seconds. And that's going to give us a value of about 27.3 meters per second. Okay, so now let's take that and put that over here. And we filled in our chart. How about that? Okay, we've got all the information we need now to get anything else. Let's take a look. Part C says, determine the magnitude and the trajectory of the initial velocity. Okay, well, they are talking about this right here. I'm going to draw a little picture. Here's the ground, here's the football, and when it leaves the kicker's foot, it has this initial velocity. And it has, because we have to have direction too, has this angle of trajectory. Now, we just found out that we have a horizontal initial velocity of 27.3 meters per second. And we have a vertical initial velocity of 10.8 meters per second. Now do you see where we are? All we have to do is use right triangle trick. So here we go. The initial velocity is going to be the square root of 27.3 meters per second squared plus, here we go, 10.8 meters per second, and don't forget to square it. All right, so if we stick that into our calculators, we're going to end up with 29.4 meters per second for the magnitude of the resultant initial velocity. So this is 29.4, okay? Now, what about the angle? What direction was it kicked? What's the trajectory? So we're going to use theta equals the inverse tangent of opposite over adjacent. Opposite, look here, 10.8 meters per second. Over the adjacent is 27.3 meters per second. Please make sure that your calculators are in degree mode or you're going to get a strange answer, okay? So if you're in degree mode and you take the inverse tangent of that ratio, you should get about 21.6 degrees, all right? So now the resultant initial velocity is 29.4 meters per second at 21.6 degrees above the horizontal. Not below. The ball doesn't go into the ground, does it? It's above the horizontal, not below it. Whoops. Go down a little bit. There we go. That's not too bad, is it? All right. Last thing on this one. How could one determine the height of the ball at the top of the parabola? Oh, okay. We want to know the top of the parabola. Well, actually, because we have so much information now, and because of symmetry as well, there are two possible ways that we can find the distance to the top of the parabola. And we're going to look at both, and which one you want to use is your preference, okay? Either one will work for a full symmetrical parabola. So let's look at what the two ways are, okay? Choice number one. We know that the time to get to the top of the parabola is half the total time, half the hang time. In this case, that would be half of 2.2 seconds, which is 1.1 second, right? Okay, so we want to know where's the ball located vertically at 1.1 seconds, because that's when it's at the top, isn't it? So what we're going to do is we're going to use the general equation on the vertical side. Remember, vertical, because we're looking for the height. So we're going to say, all right, the distance, well, let's not say distance to the top. Let's say just height, h for height. Okay, the vertical height equals v sub o vt to the top. All right, remember we start with our initial velocity and we're going to the top. And we're going to decelerate on the way up for that time period, okay? So now we get h equals, now our initial vertical velocity, don't use this. That's horizontal as well as vertical, don't use that. Go back up here to your DVAT chart. We want to use the 10.8 meters per second, and we're going to decelerate from that for 1.1 seconds by increments of 9.8. Don't forget to square the last t. All right, so here we're going to get 11.8. Actually, I think you get 11.88. I really hate rounding that, but that's going to be meters because the seconds cancel. Let me show the seconds canceling. All right. And here the second squared and the second squared are going to cancel too. So we get 11.8 meters. Now remember, don't forget that minus sign. You are slowing down, so you have to take away from that. So we get 1/2 of 9.8 is 4.9 times 1.1 squared. So 4.9 times 1.1 squared is about 5.93, I think. So now if you subtract, the height to the top of the parabola is about 5.95 meters, or about 6 meters. Okay, not so bad, is it? All right, let's look at the second way. See, we can use the fact that it takes half the total time to get to the top. Where's the ball vertically located at that point in time? Okay, the second way is the fact that we know that at the top, the vertical velocity at the top is 0 because you slowed down to a stop, didn't you? You started at 10.8 meters per second and you decelerated to 0 That means we can also use the alternate equation going from initial to what I'm going to call our final here. Now, it's not the final for the whole trip, but it's the final for the part we're looking at. So look what I'm going to write now. This is the alternate equation. The vertical velocity at the top squared, that's our final, minus the initial vertical velocity squared equals 2g, because it's vertical acceleration, times h, the distance to the top. Okay, so we're going to start with our initial vertical velocity, decelerate to 0, and that's going to tell us the vertical distance between where we had those two velocities, or in other words, the maximum height to the top of the parabola. Okay, so now the vertical velocity at the top is 0. So if we divide the 2g over, we get h equals negative v sub o v squared over 2g. So that's going to be negative, what was the vertical? Oh yeah, 10.8 meters per second. Don't forget to square the 10.8 over 2 times negative 9.8. Now look, your negatives cancel. That makes sense because you're going up to that height. That's a positive direction. Stick that into your calculator. 10.8 squared divided by 19.6. All right, this is 19.6. So 10.8 squared divided by 19.6. Guess what you get? You get 5.95. So look, 5.95, 5.95. Both are accurate descriptions, albeit different descriptions of the same motion. Okay? And it is your choice which one you would like to use. All right? You can use the time to get to the top, which is half the total time, or you can use the fact that it starts with its initial velocity and slows down to a stop at the top in the alternate equation. Either one is correct. You just have to make sure you use it properly, okay? All right, now I've got one more example here. And we're going to go through this one quick. This one's a little more like what I was talking with the second one, but we don't have to resolve it. It's already been resolved for us. It says a golf ball is projected down a fairway. The vertical component of its initial velocity is 20 meters per second, while the horizontal is 74. And they ask for these three things. So the first thing I'm going to do is make my DVAT chart. So let's do that real quick. So I do that, and then I split that in half because we need 4 lines, and I split that in half, and I split that in half. All right, so we have D, V sub O, A, T. Now, for a full symmetrical parabola, on the horizontal side, this is 0. Okay, on the vertical side, the displacement is 0 because golf balls start on the ground, they end on the ground, right? Okay, and it has a vertical acceleration of negative 9.8 meters per second squared, taking down to be negative. Okie dokie. All right, so now that we've got the inferred information in, let's come back up here. It says the vertical component of the initial velocity is 20. So we put that there. It says the horizontal component is 74. Aha! Now look, we want to determine the hang time. This. Where should we start? How about on the side with the most information? So we're going to use the vertical side to get the hang time. So we're going to say dv equals v sub o v times t plus 1/2 gt squared. All right, this term drops out. We bring let's bring this one over. This has the extra t, so let's bring that one over. So we get negative 1/2 gt squared equals v sub o v times t. Now, this t cancels with one of those two, leaves one behind. And we need to get rid of the 1/2 g and the negative to the other side. So let's do it this way. Let's say t equals v sub o v over negative 1/2 g. Okay, now if you want to multiply by 2 to get rid of the 1/2, that's perfectly acceptable as well. All right, so V sub OV is 20. And then we have negative 1/2 times negative 9.8 meters per second squared. Okay, now the negatives are going to drop out, the meters drop out, and one of the 2 seconds drops out, and the other one pops up to the top. So we end up with seconds of time. So we get 20 divided by 4.9. That's going to give us 4.08 seconds. So there's the time. Now let's put it over here. Remember, it is the same for both motions because both motions take place concurrently. All right. Part B says determine the range. That's this. So now we're going to work on the horizontal side. So to get the range, we're going to say DH equals V sub OHT. What's your subscripts? We're now working on the horizontal side, not the vertical side. This part drops out because we have constant velocity. And DH is going to be 74 meters per second for 4.08 seconds. And that's going to give us a range of, I think, 302 meters. Ta-da! That wasn't so bad, was it? Let's put that up there now. There we go. Not so bad. Okay, now let's take a look at the last part. It says determine the maximum height the ball reaches. How high did that golf ball go? Now remember, in this case, there are 2 ways we can find it, and you can choose which one you want. Okay? Remember, the first method is using the fact that the time to get to the top is half the total time. So that would be 1/2 of 4.08. And that would give us, I don't want to go too far that way because I'm going to do both methods for you so you can see. That would give us 2.04 seconds, okay? So now we're going to go the height to the top. We start with our initial vertical velocity, and we're going to travel for the time to get to the top, plus 1/2 our deceleration times the time to the top squared, okay? So now we get 20 meters per second times 2.04 seconds plus 1/2 times negative 9.8 meters per second squared times 2.04 seconds quantity squared. Okay, let me push it up a little bit for you. All right, if you multiply this out, you get about 40.8, and that would be meters because the seconds will cancel, minus, because you have a negative there, 4.9 times 2.04 seconds squared. You end up with 20.4 meters there because the second squared here cancels with the second squared there and leaves behind that meter. So we get meters minus meters, which makes sense because we're measuring distance. So 40.8 minus 20.4 is 20.4 meters. Now, the second method is always a good check. So we know that the vertical velocity at the top is 0. And we're going to decelerate to that from our initial 20 meters per second. So we're going to say the vertical velocity at the top squared minus the initial vertical velocity squared. Remember, we're going to use the alternate equation now, equals 2gh, the distance to the top, the height. This drops out because we're stopping. So we get negative v sub ov squared equals 2gh. Since we want to find h, we got to get rid of the 2g to the other side. So we get negative v sub ov squared over 2g. So that's going to be 20 meters per second, quantity squared, over 2 times negative 9.8. All right. The Seconds squared are going to cancel, and 1 meter is going to cancel and leave a second meter behind, okay? Because we got meters squared and meters. So we end up with meters. We're okay. The minuses cancel. You get 20 squared divided by 19.6. And when you do that, you get 20.4 meters. Just like we did over here. Woohoo! How about that? Pretty cool, huh? All right. So that wasn't so bad, was it? Excuse me, sorry. All right, so you are going to be working on these problems today, and I'll help you. If you're at home doing this online, guys, I cannot stress messaging me enough if you have questions, and you are going to have questions. That's just the way it's going to be. Now, don't forget, if they give you the resultant initial velocity, if they say the golf ball was hit by the club and its initial velocity was X number of meters per second at an angle of 50 degrees, guys, you have to break that down. That's the horizontal and the vertical pieces right here combined. So unless you're going to use calculus, you can't use them already combined. You have to separate them out using resolution, okay? So that you can put each one on its proper side of the chart. All right, good luck. If you have questions, don't be a ninny-muggins, ask, okay?